Okay, good. Well, I'm the first of 4 speakers now who are going to review the physics goals of the Linear Collider. And the charge I was given by the organizers was to review the subject of Higgs physics at the Linear Collider. Well, Paul Grana's already emphasized in his talk this morning that Higgs physics is really a key part of the motivation for this machine. And I think there are very good reasons for that, which I'd just like to summarize on this slide. I think at the moment we're at a crucial point in the study of fundamental physics. In the 1990s, we confirmed the standard model, the SU2 cross U1 cross SU3 gauge theory of strong, weak, and electromagnetic interactions. We really have now a great deal of confidence that that theory is a correct description of these interactions. But at the same time, that theory is not complete. It requires spontaneous symmetry breaking, and that spontaneous symmetry breaking has to be generated by something which is outside the pure gauge theory. And that is the thing we refer to as the Higgs sector. We have theories of the Higgs sector, but I think it's incorrect to say that the Higgs sector is described by any kind of standard model. It's not touched by any experiment, and we have to make experiments there and find out what's inside. Particles of the Higgs sector should be accessible at the Linear Collider, and in fact will be accessible to precision studies. And the challenge for those people who are thinking about linear collider physics is how to use that precision to wring out the secrets that these particles are hiding. So what I'd like to do in this talk is to describe work that's been done, to say what those experiments are, what they might yield. Here's a little outline. First of all, I'd like to discuss the question of where the Higgs particle or particles are. Then talk about the properties of the standard model Higgs and the reaction E plus E minus to Z Higgs. Then talk about E plus E minus to 3-body Higgs reactions. Then, hopefully time permitting, talk about extended Higgs sectors and the study of Higgses in gamma-gamma collisions. Well, first of all, we have to start with the question, must there be a Higgs sector? Is there something there that we're spending all of this money, time, and effort looking for? And I think in addressing that question, the first thing that you have to come to is what we already know about the structure of interactions. In fact, we have to go back to this very beautiful study at LEP and SLC of the properties of the Z0 and what that tells us about the nature of the weak interaction gauge theory. Those studies have verified the universality of the Z0 couplings. That's reflected, for example, in the beautiful understanding that we have now of the Z line shape, which depends on every individual species of the standard model coupling with the same coupling constant in front of T3 minus sine squared theta W times Q. We've measured both indirectly through loop corrections and directly at LEP2 the Young-Mills structure of the W couplings to gamma and Z. This data, which has just appeared in the last few years at LEP2, for those of us who've been spending 20 years thinking about E plus E minus to W plus W minus, it's just amazing to see that the world really works that way. But please remember that these curves over here are what you get if you leave out the Young-Mills interaction. And by direct study of the event shapes in WW production, one can actually tell that the vertex that's involved is the Young-Mills vertex to few % accuracy. So we know that this is a gauge theory. And that has another implication. In Young-Mills theory, only the transverse components of vector bosons are physical. If you want to make a vector boson massive, you have to borrow the third spin component from someplace else. That place is outside the gauge theory. It's a new sector in physics, a new type of interaction. And there's something there. We have to find it. Now, the success of precision electroweak fits, and maybe I should say the failure to find new particles at LEP2, which means that any new physics that could be added to precision electroweak fits has to be very heavy. motivates us to assume that new physics beyond the standard model is negligible when you analyze precision electroweak. If you make that assumption, then you can fit for the mass of the standard model Higgs. And in fact, the precision electroweak fits only work to the precision of the measurements if the Higgs turns out to be very small. Here's a contemporary ST plot plotted against the ST region, which is given by the standard model. I guess what the LEP electroweak working group is saying in the write-up from the summer is that M Higgs is less than about 220 GeV at 95% confidence. Those of you who've been following this know that this number has bounced around by 40 or 50 GeV over the last year. That actually has nothing to do with the electroweak experiments. It has to do with new evaluations of alpha of MZ. And maybe I should say this game is not completely finished. But in any case, the precision electroweak fits, under the assumption that we can do a standard model fit, really does restrict the Higgs to be less than 200 or something GeV, some place where that particle is very accessible to the linear collider. I guess one might ask about the effect of the new NuTev measurement, so I've included a slide on that. NuTev has almost the same dependence on the top Higgs and new physics processes as the direct MW measurement. So it's useful to compare them, and here's the comparison on an ST plot. If you throw NuTev into the global fit, the contour that I showed on the last slide changes to this contour, and it still, remember this is the 200 GeV line, strongly favors a light Higgs. In my mind, the most likely explanation for the discrepancy in NuTev is that parton distributions aren't as simple as you would like. Even in an isoscalar nucleus, U is not equal to D, S is not equal to S bar. That can generate a systematic shift of the NuTev prediction, which is actually sizable in the size of the discrepancy. Of course, the most interesting explanation is that NuTev is found as E prime, which then will show up very early in the run 2 at the Tevatron. And so this is the one we'd like to happen. This is maybe my more pessimistic point of view. In any case, I don't think NuTev has any effect on the conclusion of the previous slide, that precision electroweak favors a light Higgs. Now, it certainly is true that the assumption that the standard model can be used to bound the Higgs is not true in every model. And actually, in most models, actually you get a stronger constraint on new physics than in the standard model. But there are some specific counterexamples. I guess most of you in this room have heard this story. Jim Wells and I actually wrote this up in some detail, and we've lectured on it several times in the past year. Those of you who haven't heard the story should read our paper. But for the purpose of this talk, I'm going to say, let's assume that the precision electroweak constraint really should be taken seriously. Then there's a particle that we should be chasing after. I remind you that the precision electroweak constraint involves mainly this Feynman diagram, which requires the coupling of H to two W's. This is exactly the coupling by which the standard model Higgs boson gives the W its mass. And so we need a particle which is light, roughly less than 200 GeV, which fits the profile that it includes this particular coupling. Now, aside from the direct experimental measurement, if you go into different theories, you can find independent upper bounds on the mass of the lightest Higgs boson. In the standard model where the Higgs is an elementary field up to a certain scale, that actually gives you a different and quite separate argument. If the Higgs is effectively an elementary field up to a scale lambda, it starts with some self-coupling. That self-coupling is renormalized to smaller values by the renormalization group as you come down to the TeV scale. And of course, the mass squared of the Higgs is proportional to that coupling. So the mass of the Higgs then gets an upper bound. Very roughly, the upper bound is given by a formula that looks like this. So it involves in the denominator the log of the high scale up to which the Higgs is elementary. If you just plug in a value like 10 to the 16th GeV, the number again, this is, please remember, completely independent of the previous argument, comes out to be about 200 GeV. Actually, in the context of supersymmetric grand unified theories, theorists have made an extensive search for models in which the Higgs mass goes as high as possible, but still is subject to the renormalization group physics that I've described here. The world record to date is a mass of 208 GeV, which is given in this paper. It's a model with heavy singlet and triplet Higgses, where both of those new types of new fields feed into the renormalization group equations in various ways. But the argument given here is very loose. This is a very approximate formula. But it turns out that when you really do the analysis, it's quite rigid. It's very hard if you have grand unification, if you really have a scalar Higgs, which generates mass, to generate a very high value for the Higgs mass. Now, a very important special case is the minimal supersymmetric standard model. In this model, there's actually, well, let me define that model. That's a model which is supersymmetric, which has a Higgs structure of a Higgs for the up quarks, a Higgs for the down quarks, and no SU2 singlets. In that model, there's a very special structure to the Higgs potential. As the supersymmetric masses become large, you get the simplest case. There's one mode, which is given here, that basically is unsuppressed, has no potential from all of the extra physics that comes with supersymmetry, except for what's called the SU2 cross U1D terms, which depend only on the gauge couplings. So for this mode, you can actually compute the potential, and it turns out that the Higgs mass must be of order the Z mass. In fact, at tree level, you get this relation. Well, it's well known that loop corrections are very important. They involve, in particular, the fourth power of the top quark mass and a logarithmic enhancement from the supersymmetry scale. But nevertheless, this term can only push you so far. The absolute upper bound, now evaluated to the 2-loop level, is about 135 GeV. But frankly, when you get above 120 GeV, you have to really stand on your head to push the Higgs mass that high. I think people who believe in the MSSM probably should believe that LEP observed the Higgs at 115 GeV. And this gives a very sharp question that CDF and D0 hopefully will answer in the next 3 or 4 years. I hope the answer is positive. Well, now let's talk about experiments on the Higgs. The place that I like to start is E plus E minus to Z0 Higgs, a very simple process, a very highly constrained environment to study the properties of Higgs bosons. You find a Z at a definite lab energy. What's on the other side is the Higgs. Finding the Z absolutely normalizes the cross-section, and what you see on the other side measures the branching ratios. Of course, to really do it in practice, it's much more complicated, but to start from a very simple and definite place has a lot of advantages that one can build on for precision studies. I should say that most studies of this process that have been done assume that the Z decays to leptons. Of course, the branching ratio of the Z to leptons is 7%. The branching ratio of Z to QQ bar is 70%. People multiply by a factor of 4 in the statistics or something like that, assuming that you can translate this into an enhancement of this. Clearly, as the better you can do in calorimetrically defining the Z, actually also measuring the Z polarization is important by resolving the two-jet system. The better you can do on this process, the larger the statistics will be, and there's a big advantage there. And this is something that really needs to be studied in a very serious way for all of the Higgs detection modes, how good a calorimeter you need and how to really get the best of this advantage. The dominant background comes from E plus E minus to 2Z production, where one or both of the Z's are off shell. This highlights the importance of the polarization analysis. In this process, the Z is dominantly longitudinally polarized. Here, the Z is transversely polarized. And so if you can resolve the jets or the leptons, there's something you can win. I'll just show you a few simple slides from that. Here's the cross-section in femtobarns. The simple cross-section, and then with beam effect, Z-width, etc., ISR. Clearly, there's an advantage in working near threshold, but that advantage, frankly, isn't so great if you look at the numbers, especially if the luminosity of the collider naturally increases proportional to the center of mass energy. I think probably a better way of thinking about it is that as you do the linear collider program, at every energy you'll measure the Higgs. And somehow you want to put all that data together to get the highest statistics on the properties of this Higgs reaction. Here are the lab frame energy distributions for E plus E minus to Z Higgs. This is really a pretty rough cut. I didn't, for example, put any restriction on the mass of the Z, which would lower the background considerably in this region. But here's the comparison between the ZZ and this rather rough cut Z Higgs in this peak. You can see it's quite a large effect even at this level, one that's easy to pick out. And maybe I should also say that since the background is electroweak, we know exactly what it is to parts per mil. So one can read off this enhancement with some good precision. I think already at SNOMES 96, Rick Van Kooten argued that one can measure the enhancement here to a few % of the standard model value. Now, from this kind of analysis, you can measure the E plus E minus to Z Higgs cross-section. And I think it's important to emphasize that this is not just an ordinary run-of-the-mill cross-section, one of many that you would like to determine. This cross-section really has important physical significance, which I'd like to emphasize. Let's remember that in the standard model, the Higgs coupling to W and Z has this structure. It's just proportional to the W and Z mass squared. And that's no surprise because, of course, if you give this guy the vacuum expectation value, that the same diagram produces the mass of the W and Z. In a multi-Higgs doublet model, let me assume for simplicity that all the Higgses are doublets, you would have a contribution to the W and Z mass proportional to the gauge couplings, and then the Higgs vacuum expectation value. And so you get the rather simple result that the cross-section for Z and a particular Higgs divided by the predicted standard model cross-section is the square of the ratio of that Higgs expectation value to the total 246 GeV that gives you the mass of the W. That is, this cross-section tells you what fraction of the Z mass comes from the Higgs that you have discovered. In principle, you should learn that for every Higgs in the theory and verify the sum rule that these particles sum up to the total mass of the Z. Let me note also what follows from this relation, which is sometimes useful to normalize branching ratios. If you measure the Higgs to W plus W minus branching ratio, and you measure this vertex in some way, that gives you a way of normalizing the branching ratios of the Higgs. The fermion couplings to Higgs have a similar quality. In the standard model, where a single Higgs generates all the masses, the vertex is the mass of the fermion divided by the vacuum expectation value. Again, a simple consequence of the fact that this vertex is where the mass comes from. If there's one Higgs boson, its couplings are proportional to mass. To the extent that the branching ratios match or do not match with the standard model values, you test that assumption explicitly. The Higgs couplings to gamma, gamma, and glue, glue are a little more complicated. They're generated at one loop. They have the form of sum rules over the particles that get mass by electroweak symmetry breaking, which are heavier than the Higgs. Those in the standard model are dominated by top, and for the gamma-gamma case by W, but in principle, heavier states which get mass from the Higgs mechanism can appear here, and in fact in order 1 in these sum rules. For a light Higgs, here are the branching fractions, and you can see that above the 1% level, there are a lot of interesting modes that come in for a Higgs, let's say, of 115 to 130. One can imagine measuring essentially everything down to this level, and because gamma-gamma is quite characteristic, also gamma-gamma can be measured with, let's say, 500 inverse femtobarn type yields with a reasonable accuracy. I'll put all these numbers on a slide later. In a 2 Higgs doublet model, such as the MSSM, one has variations of these vertices, which have the form that I've written here. In a general two Higgs doublet model, one might expect, for example, large deviations to the branching ratio to up quarks, like charm, to the branching ratio to down quarks, like bottom. So that ratio is something that can tell you how close you are to the idealized 1 Higgs limit. In the MSSM, actually, unfortunately, these ratios tend to be very close to 1. This, again, is a consequence of the very special structure of the Higgs potential in the MSSM that I referred to before. So if cosine of beta minus alpha is small, these ratios are close to 1. And in the MSSM, the tree level relation is something like this. As the heavy Higgses become heavy, this angle decouples. For that reason, in the MSSM, it's important to include not only the tree relations, but also the radiative corrections. In fact, both from the standard model sources and from supersymmetry. And in the past year, that's been pursued by many people, in particular Heather Logan and her collaborators at Fermilab. And so there you find a lot of surprises. One of the most interesting ones to me is that even though it doesn't seem here that there would be a difference between, let's say, down quarks and leptons, bottom and tau, in fact, you can generate large deviations from the standard model relation in those from the radiative corrections. Actually, maybe I should say this would have been clear to me if I'd read this paper, but these guys have re-emphasized this point. Here's some results of that study, and what you can see is that it's, in fact, quite straightforward in the parameter space of the MSSM to generate 3%, even 10% corrections to what you see here are the B, W, and gluon branching fractions. Many people give emphasis to the spin in CP of the Higgs boson. Well, let me just repeat some basic things about this. First of all, only a scalar, that is 0 and CP plus, can couple to the WW and ZZ systems in a way that gives mass to these particles. So roughly, if you see a cross-section of order of the standard model cross-section, the particle that you're seeing is either a scalar or dominantly a scalar, as opposed to a pseudoscalar. The scalar coupling gives characteristic dependences on the center of mass energy, cosine theta, and the Z polarization, all of which can be directly tested experimentally. The d sigma d cosine theta is quite close to sine squared theta, as you would assume for two scalar production. The Z is longitudinally polarized. Both of those things can be checked directly in the experiments. Another thing that you might ask is, does the Higgs have, although it's dominantly scalar, a CP-violating admixture of pseudoscalar? It's a very interesting question, and that question is harder to get at. Roughly what this does, a small admixture of a pseudoscalar, which would be CP-violating, is to put a phase into the helicity-dependent vertices. Unfortunately, unless you have interference between the left and right-handed particles coming out, you can't visualize this in experiment. So, for example, it's very difficult to see this phase if you look at the final states in bottom-bottom production. However, there's an interesting and rather subtle effect pointed out many years ago by Kramer and collaborators in the Higgs to tau decay. When the taus decay to 2 pions, the dependence of this system on the angle of the pi nu systems on the two sides of the Higgs actually is sensitive to this phase. It's a quite subtle effect, but it's really there. Here's a simulation of it. The two lower curves are the difference between pure H and pure A for the pi-pi decay. Don't mix in the rho decay, because there's much less sensitivity. No one, as far as I know, up until now has really tried to see, these are very small angles. So what's here is the ratio of the angle to a full just pi back to back as the taus come out. So it's quite a challenging measurement. Gary Bauer at SLAC has been studying this, and Zbigniew Voss, the author of Tau Law. And I think they're both going to talk here in the Higgs session on whether this actually is observable. If it could be seen, it would really be a nice thing to check directly CP admixtures of the Higgs boson. For heavier Higgses, I just want to say a few words. There certainly has been much less simulation work on heavy Higgses, but there are some interesting things to say. The phenomenological picture is quite different. So here is that same set of branching ratios, but now in a different slice of the standard model Higgs mass, from 140 to 220. You see here, the WW mode of the Higgs becomes dominant. Above 180, the ZZ mode kicks in. They both basically cause the width to become large, now hundreds of MeV at this point. The bottom width goes away, but not completely. Bottom is still there as a rare decay at 200 GeV, a couple times 10 to the minus 3. And in fact, one can still check the ratio of the fermion to the W contributions as a fundamental measurement. It's tough, but there's been some work on that. Battaglia and Desch showed this slide at the Warsaw meeting, where, for example, they chose a 200 GeV Higgs analyzed at an energy of 350 GeV. You start with an event sample that looks like this in terms of the various contributions to the Higgs branching ratio. You use the fact that W's don't decay to bottom quarks. So if you do stringent bottom tagging, you end up with a much smaller sample. It's hard to read these numbers, but it's a much smaller sample, but which is now dominated by what's in red is the BB width. And they claim actually a coupling constant determination of 15 to 20% for a 200 GeV Higgs. So there's something that can be done there. It's interesting to study. For the mass above 350 GeV, of course, if the Higgs should unfortunately end up there in violation of the precision electroweak constraint, the mode Higgs to TT bar becomes relevant. Here's again that rather simple curve. It comes up to an asymptotic value of about 20%. And the interesting way to measure it, as pointed out by these authors, is to look at E plus E minus to nu bar TT bar, where the Higgs comes in as an S-channel resonant contribution that actually dominates this process. Okay. There are some other processes which are interesting for the study of a light Higgs. A very important one is WW fusion, E plus E minus to W pairs, ending with to W pairs plus neutrinos, where the W's then fuse into a Higgs. Again, this diagram, like the diagram for E plus E minus to Z Higgs, depends on the vertex that gives the W boson's mass. And so the absolute normalization of this cross-section is physically extremely important. Like this process, it depends on exactly the fraction that this Higgs contributes to the W mass. If M Higgs is known, this process is very clean. You look for a hadronic system in the detector that has the known mass of the Higgs and nothing else. That nothing else comes from electroweak sources, which are precisely computable. That's probably the main advantage of the process at linear colliders over the similar process at the LHC. And so one can pick out this signal. Also the cross-section, actually, I put these on another slide, whereas the colors are hard to see here. This is the cross-sections for E plus E minus to Z Higgs at 500 and 800 GeV in the center of mass as a function of the Higgs mass. The blue is the cross-section for the W fusion process at 500 and 800. So you see that there's some increase with the center of mass energy, which is actually a logarithm of the center of mass energy. Actually, among the interesting statements in the literature about this process, Battaglia and Derouk have suggested that if you go to really high energies, you get enough events that you can see the Higgs to mu plus mu minus branching ratio and actually measure it quite accurately. Okay. There are two more important three-body processes which give you other handles on some of the Higgs couplings. E plus E minus to TT bar Higgs. This has a cross-section of about 2 femtobarns at a center of mass energy of 2 TeV. But if you really get a large event yield, 1,000 inverse femtobarns, let's say, you can do something with it to make a precision measurement of the Higgs top coupling. And E plus E minus to Z Higgs, which has been proposed seriously by these authors as a way of measuring the Higgs self-coupling. It's a tough experiment, a tenth of a femtobarn cross-section at 1 TeV. But nevertheless, with calorimetric identification of everything to really maximize the event yield, it's claimed that you can do it and actually get a measurement out of this process. So here is, I guess, the current estimates of the accuracy of Higgs coupling determinations as a function of the mass of the Higgs in this column and the coupling going down this side. These two lines have to do with the coupling determination from the cross-section for E plus E minus to Z Higgs and W fusion production of Higgs. Then these down here are the branching ratio measurements, for which I guess you have to add in what I've given are the errors on branching ratios. And so you have to add in quadrature the thing that normalizes the branching ratios, either the absolute cross-section or the Higgs to WW cross-section. And then down here, these very ambitious ways of measuring the top coupling or the Higgs coupling. All of the numbers reflect 500 inverse femtobarns at 500 GeV, except for the starred ones, which are 1,000 inverse femtobarns at 800 GeV. There are some numbers here which are, there are certain numbers here which are given in red. And I think those actually deserve some comment. Typically here, the lower number is what appears in the ECFA-DAISY study. The higher number reflects the attempt of the University of Oregon group to reproduce those numbers based on full simulation and use of the tools similar to the SLD tools to do reconstruction and pattern recognition in those events. The discrepancy between those numbers says that there's a lot of work to be done in this respect to figure out, basically, given some ideal goal that we should be able to reach in terms of the accuracy of measuring these Higgs branching ratios, how do we develop the tools to really go and do it? So that's what's said on this slide. Maybe I should also say that the Oregon group has a more conservative treatment of the ZZ background, and there's something still there to be understood as well. But it seems that much more work is needed in terms of the detector, the algorithms for reconstruction, the proper use of energy flow in calorimetry, and really what are the optimal methods for doing these measurements. Okay. Well, now there's unfortunately just a little time left, but let me say some things about topics connected to heavier Higgses. First of all, I'll remind you a little of the 2 Higgs doublet spectrum. This again starts with 2 Higgs fields, which are doublets of SU2. The states of those fields are listed here. A little h and a capital H, which are neutral and CP even and mix with an angle called alpha. A CP odd state called A0, and this is actually a true Goldstone boson of SU2, mixing with an angle called beta, which is actually exactly the ratio of the 2 Higgs expectation values. And then a charged Higgs pair and another pair of Goldstone bosons. The things in brackets are eaten by the W and Z when they get mass, and the other particles listed are physical and observable. In terms of these angles, the coupling to W, W, and ZZ are given like this. The little h with the sine of an angle, the capital H with the cosine of an angle. So the sum of the squares is 1, and this is the sum rule for the E plus E minus to Z Higgs cross-section that I referred to earlier in the talk. I think I listed these relations earlier in the talk, and here are the comparable relations for the heavy Higgses. Actually, in view of the time, I'd just like to go to the special case of the MSSM. Here, I've already explained that the little h must be very light, and in fact has a mass which is bounded. But the heavier Higgses are typically heavy. In various supersymmetric models, they can range from 200 to 600 or even higher in mass. As the mass of these particles all get heavy together because of the special structure of the potential, and as they get heavy, cosine beta minus alpha becomes small, and the HA mass difference becomes small according to this relation. If you evaluate that number, it's a few GeV. It's actually comparable to the widths of H and A. This situation has a special phenomenology. The capital H decouples from W pairs. Its dominant production mechanism is actually the pair production with the A, where these two particles have almost the same mass, and when you plug into the previous formulae, also almost the same branching fractions. In both cases, the BB bar mode is enhanced by tan beta. The TT bar mode is suppressed by 1 over tan beta. Actually, these equations are extremely interesting because they say that by measuring the branching ratios of the heavy Higgses, you get direct access to this parameter tan beta, which is, of course, ubiquitous in all the formulae of supersymmetry. There's not been so much work on experimental studies of these. Here's something that was just presented at Snowmass. The Helsinki group showed a reconstruction of the charged Higgs in TB bar. But maybe more relevantly is a question of how well you can do in this tan beta measurement. From some time ago, there's a study by Feng and Moroi, and here's a typical slide from that study. The conditions here are MA of 300 GeV, a center of mass energy of 1 TeV, and luminosity samples from the outside to the inside of 200, 400, 600, 800. You can see that in the region where the BB bar and TT bar decays of H and A are comparable, you get good discrimination of tan beta. As one mode dominates, for example, up here, the BB bar dominates, you need higher and higher statistics to determine tan beta in that region. If you look at this paper, it's quite nice, but I think without any shame to these people, this study really ought to be repeated by an experimentalist. And I think it's a challenge to someone in this room to show what, with a realistic detector and some kind of more realistic B-tagging capability, how one can do in this kind of measurement. Well, finally, let me discuss the appearance of the Higgs in gamma-gamma. Since H0 and also the heavy neutral Higgses decay to gamma-gamma, they can be found as resonances, S-channel resonances at a gamma-gamma collider. The decay widths are very small. Remember, these branching ratios are 10 to the minus 3 typically. But if you see it as a resonance in the S-channel, you get that factor of 1,000 enhancement back, and you come to something that's of order 1 with respect to other standard model processes. You can further make use of the characteristic gamma-gamma luminosity spectrum, which you can adjust by adjusting the center of mass energy to peak up right where the Higgs is. So in the case of a light Higgs where we'll know the mass, we'll know at what center of mass energy we should be operating the gamma-gamma collider. You can use B-tagging to suppress gamma-gamma to CC bar. Of course, gamma-gamma to BB bar is suppressed because the B has a small charge. And if you polarize the gammas in the JZ equals 0 state, you can further suppress 2 fermion standard model production, because this dominantly occurs at high energy in the J0 equals 2 state. So using all of these advantages, you can really arrange that the Higgs resonance stands out. Actually, in the past year, there's been a very intensive study of this, motivated by the technical development of gamma-gamma colliders at Livermore, and I refer you to this new and interesting paper. Here are a couple slides from that paper. Here's what these people, Asner, Grönberg, and Gunyon, expect is the signal of 120 GeV Higgs under the correct running conditions, which would be 160 GeV in the center of mass, maximizing the E- polarization, and adjusting the polarization state to maximize JZ equals 0. It's quite an impressive signal. They claim a determination of the absolute partial width of Higgs to gamma-gamma to about 3% accuracy in this study. Now, what's even more interesting is that the heavy Higgses appear singly. So at a lower center of mass energy, you can produce the heavy Higgses and, in fact, be quite sensitive to their properties. If we had the MSSM and the Higgs is as heavy as 115 or 120, you're driven to high tan beta. And please notice that that enhances the appearance of the Higgs signal on top of a background, which in this case is actually dominantly charm from the electromagnetic process with a mistag identifying it as a B. So perhaps there's even further work that can clean this up. In any event, this study is something that's very promising for the future, I think both for the gamma-gamma technology and for our eventual knowledge of the properties of these heavy Higgs bosons. At a photon-photon collider, you can not only have longitudinal polarization, but you could also imagine working with linearly polarized photons. And that has another interesting effect on the H0A0 system. Linear polarization is the thing you use to determine whether a Higgs is a scalar or a pseudoscalar. That is, whether it's produced in this polarization state or this polarization state. But in fact, you can also use linear polarization combined with study of the final state to produce interferences between H and A. And there's a very interesting paper, which I refer you to if you're interested in such things, where these authors show how to use linear polarization to make the H and the A interfere, to very precisely measure the mass difference as well as the widths of these particles. Okay, well, I guess that's what I have time for in this review, so let me just summarize. The Higgs particles stand outside the standard model, but they are essential to its structure. We really don't know anything about them from direct experiment. We have to go find out. And this is really, it seems to me, the next big chapter that's coming in particle physics. The linear collider offers many experimental probes of these mysterious particles. And what's especially interesting to me is how directly these probes impact the very nature of the Higgs boson. They really allow us to tell directly, does the Higgs boson give mass to each individual species of quark and lepton? In principle, we could answer that question affirmatively, or more interestingly, find that the answer is negative and that there are still more things that we have to understand. And I think the level of detail that the linear collider makes available allows us to search for clues to the deeper mystery of the origin of these particles. So thank you very much.